All right, so I think this is going. All right, welcome to Houston Functional Programmers. I'm Ryan Riley. I work for a company called Tachius, and we optimize energy production for upstream oil and gas companies producing oil from oil fields. We're using F# for almost our entire stack. We have some MATLAB doing some modeling. We have like F# doing a lot of data munging and crunching and analytics and piping up stuff, things up into the front end. We have a TypeScript web client that's consuming the outputs that our F# does. So for this talk, I'm going to be talking about extending F#, which is a kind of a dialect of OCaml that runs on the .NET platform with computation expressions. Computation expressions are a feature of the language. I'm not going to be doing a deep dive in this talk. This is more showing kind of how they work, use cases, how they can be used, and really the flexibility of this. So who's familiar with something like the OCaml module system? Okay, so it's kind of a system for kind of leveling up, right? You have functions and variant values and things like that at the lower level, and then you have the modules where you can actually transform from module to module using functors. That's an ML and an OCaml methodology for doing that sort of thing. Who's familiar with Haskell? Type classes and those sorts of things. So computation expressions try to give you some ability to encode things like that. But if you have those in your head, it's insufficient to capture all of what computation expressions allow. So as we get started, I gave this talk a year ago at Open F#, and it was to a bunch of people who were coming to talk about F# and learn more about F#. The prerequisites I had then were that you were basically familiar with the language, you were familiar with basic pieces of how F# works, you've coded some in it. I don't have that as a base for this, but I'm not planning on going to like a lot of deep detail about syntax. So if you do have questions, as you ask, please feel free to interrupt me, ask a question about like, what's that let keyword mean, or what's this other thing mean? Keywords in particular are a big topic here because we're talking about how computation expressions, the strict form, stick with the general keywords and syntax of the language, but also look at how you can actually inject your own syntax into the language through some extensions that this provides. So if something doesn't look familiar, just ask and we'll definitely dig into it and talk about that more. I might pause you and say we'll get to that in a few slides, but that's kind of the baselines. Motivation. Why talk about computation expressions? Why have computation expressions? So we already talked about like Haskell and OCaml, things like that. One of the things that the computation expressions also bring in is something like LINQ, so language integrated query in the rest of .NET, where you have the ability to write queries over different data sources and retrieve things in. And in general, when you're writing programs, you want to have the flexibility to write your own programs in the way that you want and express it in a succinct and meaningful way. So when you come back to it, you can easily read it, you can understand what you're doing, you can write it. And computations actually add a lot of value in this way, again, as we'll see here very quickly. The topics we're going to be covering include computation expressions, obviously the topic of this talk. The computation expressions in their kind of strictest form is like a subset of what is generally available in computation expressions. So I'll kind of differentiate what's supposedly a strict computation expression from what we'll also see is called a query expression. There's also type extensions that can play into usage of computation expressions and query expressions. And then this one, I think most of you should be familiar with, domain-specific languages. So computation expressions allow you to embed domain-specific languages within F#, and that's really one of the most powerful pieces that are offered by computation expressions. So we'll look at some examples of that towards the end. So starting off, when you first get into F# and you start using it, you'll see things like this. So you see a sequence expression. The sequence is essentially a lazy list and enumerable, if you're familiar with the .NET framework. And this is kind of like a comprehension if you've used like Python or some other languages where you can put sort of brackets around something and say for a value within a range, do something with that value, right? So this is a very simple one where we're just, for every number in a sequence, we're going to just return that number. The comprehension syntax uses this arrow notation, but you can expand that to do yield. And that's important because the yield is actually part of the computation expression syntax. So these list comprehensions, sequence comprehension, array comprehensions, they're all built into the language. They're not part of computation expressions, but they do have the longer form syntax of like do yield that you can see there. Yes, sir.
Basic question. That 1 colon, does that just mean like that's a line on the bottom? That's the output of the line? Or like
one?
No, like the very beginning. Is that
Yeah. Sorry.
Prompt, like a shell prompt, essentially?
It's actually just like line numbers. So
Okay.
this is
and that's like the result. The second thing is a result.
Yeah.
So you have like 2 lines of code and 2 lines of result.
Yeah,
Okay.
exactly.
Thanks.
Yeah.
Just really basic.
Yep. No, that's good. That's a good question. So this slide deck is actually generated from F#. And so it has like the benefits. I think actually if I hover over some of this, you can actually see some. It always depends on how well
Like type information or something.
it's more like the screen size. If it gets shifted, the hover syntax helpers like show up or disappear. Like it's very likely that when I'm hovering over here, there's a tooltip somewhere down like to the bottom right or something that you can't see. Yeah, exactly. But there should be tooltips showing like like I is an int and whatnot. And just for reference, the 1.10 is like a range. It is implicitly enumerable, but it is not in fact an enumerable itself. Not that that really makes much of a difference. It's just kind of baked into its OCamlese that has still survived into F#. But this is a sequence. You can concatenate sequences with like the module here. So we have a seq module with an append function that takes 2 sequences and concatenates them. Unfortunately, the output didn't show up in this case. But one nice thing about the computation expression syntax is there's also this thing like yield bang. So we saw up above, there's a yield, which yields out a value. And here we can also do a yield bang. So what do you think that yield bang allows us to do?
What does yield do?
So yield yields a value. So if you're iterating, it yields one back out in a lazy sort of way. So if I'm iterating over that seek the x's,
It will evaluate the whole.
it won't evaluate the whole thing. It'll evaluate one at a time as it iterates. So yield is like, here's the next one. Oh, here's the next one. Oh, here's the next. Every time you're iterating, it's giving you the next value at that point in time.
Is yield bang not easy?
It is still lazy. Yes.
So you don't use yield bang, you're going to have a sequence of a sequence.
That's right.
This allows you to bring it up at the same level.
Yeah, it's kind of like flat map, basically. So you're basically lifting all the values of x's into the parent sequence. So it's basically doing exactly the same thing as we just saw with append.
You're combining 2 lazy sequences. Now you have 1 lazy sequence.
Exactly.
Okay.
Yeah. It's the same thing as append. You're just appending one onto the other. And this is a way of using the computation expression syntax to do the same thing. So this isn't really like miraculous or exciting at this point. It's just more to show like here's some syntax to let you do. This is not usually something you would find in like a comprehension syntax. Most of them would be using something like the yield, although they usually have like the arrow. This allows you to go a little further where you can actually lift more stuff out as part of the syntax itself.
Can you slide through that? But you don't actually write that bottom line, right? It's calculated by that program you said?
Yep.
It'd be so much more easier if that said 20 at the end.
It would.
Because you know what I mean?
Yeah.
But
So this is basically like the F# interactive output. That's what it would
yeah,
show
I
in
know.
the
Yeah,
at the
what I'm
end.
saying. From the
Yeah.
slide perspective.
Well, yeah, and even the square brackets, like you can look above and see, well, sequences have curly braces, not square brackets. So I have no real good answer for that. I don't really understand. Again, it's probably some holdover from OCaml in the past, where like lists were the primary sequence type. But there you have it. All right, so this sample, except for the URL there, and a few details is roughly 11 years old, which is funny because like async await just landed in TypeScript, what, 3 years ago maybe? It's been in C# for quite some time, but the async await type of thing, you see that this is it has an async computation expression. Async is at the top, it's got an open curly brace, some F# code, there's some lets, let bang, use, return. Most of this looks like pretty standard syntax if you're familiar with OCaml, except for the ones that have a bang next to them. Return is also typically not used if you know OCaml or F#. At the end of a function, whatever is the last expression, the return or the result of that is what is returned for the function. So the return is an explicit return in this case. And then it's piping to and this is another F#ism that's started to carry over into languages like Elixir and others where you have a forward pipe operator where you take something and basically push it into a pipeline of chain functions. So this is going to take an asynchronous computation and then run it synchronously, is what that pipe into the async run synchronously is going to do. So what do you think the bangs do here? Do you want to know, so you're going to ask about the let itself?
No, I was gonna ask the question.
Oh, okay.
So I mean, here's my guess.
Yeah.
Okay, like, so my guess is that it just lets you do like async await, or it lets you, you're signifying this is going to happen at some point.
Yep. Yeah, the bang is effectively the await. So you don't have to write await, you don't have to do that. It's just bang, and it's going to wait on that. And it's going to transform that. So where you see the bang, the let bang rest, the rest forward is going to become a callback, right? So if you can think about like writing this long form, you would have let request, you're creating a request, and you're going to say, normally, without the computation expression, you have something like rec.async get response with a lambda taking the response and putting all this stuff in there. And then here again, you have another one. So you have this arrowhead thing kind of coming out here with chain callbacks, right?
And that's the callback.
Yep.
So another guess / question.
Yep.
I'm guessing that you have to explicitly return because it's asynchronous, because the expression gets evaluated immediately, but is that correct?
Yep.
Yeah.
Well, parts of it get evaluated immediately, but at the very end, basically the return is explicitly saying, I have a return value. There are ways of saying, I don't have anything to do, but you have to kind of tell, like, how would the computation expression do something if there's no return value?
Right.
If there is no explicit return, what's the value that is returned?
Is there like an immediate return that, like, or?
It will immediately return with an async computation. So async,
Okay, right.
The async computation itself is actually lazy. Or delayed. It's not right to say lazy. It's more correct to say it's delayed. So it's effectively, you're defining something you want to do later. And in fact, even the let request at the very top is also delayed. And we'll look at like how that actually works. We'll look at some expansions of how these things expand into the long form of what actually gets run by the runtime.
It's like a JavaScript promise.
Yeah, basically. There's some differences in that a promise gets kicked off immediately, just like a task in .NET, or a lot of the promise or task type things are immediately invoked. So they start off, and you're basically going to await it later on. Promises are like that. In this case, you create it, and it doesn't get started until you tell it. Now I'm ready for you to actually start running.
I have another silly question.
Sure.
Okay, in the bottom,
Mhm.
you just have a string. It's obviously like HTML.
Yep.
My question is about string escaping.
Okay.
So like, for the duck type, we have a double quote.
Yep.
And inside that string, there's like more double quotes.
Mhm.
Is that allowed, or like is that, how does that work?
So again, this is the output of F# Interactive.
Okay.
That is not legal F#.
Okay, so it's just like a formatting quirk.
Yeah, I really don't understand how some of this F# Interactive output actually works, but this is what actually gets printed out when you run it. You could put triple double quotes around either end, and then you don't have to do any kind of difference with the content internally. Those are good questions.
Thank you.
Anybody else have any questions on this before we?
Thank you for asking all my questions.
Oh yeah, I planned. We collaborated ahead of time.
Yeah.
So you're just passing 3 years ago?
So the way I wanted to kind of focus on this is there's a number of different ways to approach computation expressions. We're going to be looking at a lot of samples, but I wanted to kind of categorize them in terms of like patterns of thinking of them. We kind of looked at the basic shape of what we're going to look at: computation expressions, query expressions, extensions, and then domain-specific languages. And in order to do this the right way, I decided we would tie it to a theme. And what better theme and what better way to introduce the theme than with a poem? So this is from The Lord of the Rings, obviously. 3 rings for the elven kings under the sky, 7 for the dwarf lords in their halls of stone, 9 for mortal men doomed to die, 1 for the dark lord on his dark throne. In the land of Mordor where the shadows lie, 1 ring to rule them all, 1 ring to find them, 1 ring to bring them all, and in the darkness find them, in the land of Mordor where the shadows lie. And you might be wondering why would I pick such a dark poem to talk about this wonderful feature in F# about computation expressions. It's a great question. And we're actually going to go bottom up. So 1 for the Dark Lord on his dark throne. We're actually going to pause here and do an async. We'll come back to this in a moment because this ties into this initial piece. So 9 for mortal men doomed to die. Most people, when they come into computation expressions, think, oh, this is the way I write monads in F#. Right? Monads are all the rage. They're the best pattern ever. They can solve every single problem, including tying your shoes, writing your unicycle, making you ice cream in an oven. And not to, deride them too much. And the topic of this talk is not to talk about monads, but we will be looking at some of this. So we'll start there. Why should we care about computation expressions? And so initially, this isn't probably the best example. It would be better if I had a more like arrowhead looking thing where I had like 10 matches going way down and then coming back out. But you start seeing a pattern here. This is using an option type. So I've got 1. I've just arbitrarily said it's sum 1. So it's an option of 1. There's a try-divide function that takes a number, a numerator, and a denominator. And if the denominator is 0, returns none. If it's not 0, then it returns an option sum of the numerator divided by the denominator. So then we match our 1. If it's sum, then we try to divide it by 0 because why not? And if it somehow manages not to be none, in this case, it will never that will never happen. But if it isn't, then we're going to add x and y together. So we're going to add the 1 plus whatever it was divided by 0. That's not going to happen, so we know it's going to be none. And you see this kind of approach at the very bottom where none, 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 and that's just kind of annoying to rewrite over and over and over. Now you can solve this with modules of functions. It's not too bad, but you end up with the same problem. You still have to then chain kind of nested lambdas calling back. You still have an arrowhead pattern either way you write this. So we could create our option monad. A monad requires bind and return to be implemented. Fortunately, F# core gives us an option module with a bind function, so we can define a computation expression here as a monad with a bind and return member. The let bang that we saw earlier is the bind, and the return is the return. So it's a pretty easy translation between the two, and this would let us get around writing that long match arrowhead pattern. In addition to bind and return, there's a bunch of other methods we could also implement. So bind and return, we also have return from. That lets us take, if we already have an option, like if we have a none, and we just want to return the none, how would you do that if you didn't have a return from, for example? Right? Within the computation expression, you're working with a value, like an int or a string. If you wanted to return none, you're now trying to lift out of the pattern. So this gives you a kind of an escape valve, if you will, to return back an option immediately without having to deconstruct it and return something else. 0 is what you would implement if you want a kind of, I don't want to return anything, I just want it to return something by default. That's what 0 is. Valid values for 0 might be sum of unit, where there's like nothing. A none, there may be other reasons why you might implement this differently. And it actually gets into some of the flexibility of these computation expressions, and that there's not always one right way or even a best way to write these. So this is one way where 0 is going to be none. There's a combine method. Combine lets you return multiple values and tells how you would do so. We'll look at an example of that in a bit. Delay tells what happens if you want to delay the computation expression, and then run allows you to specify how you want to run the computation expression. It's basically kind of an outside wrapper. So let's say you want internal to the option computation, you want to use an option. Maybe you want to use something different. Run will let you then translate that out to something else. I could also here, if I don't want this to actually return anything, I just want it to print out the result. I could actually have run the computation and print out the result and return unit. So it actually, at the end of running an option, it would do nothing at all. It just prints it into the screen. So run is kind of a top-level hatch to do something at the end. Here's some expansion. So if I just have a maybe, that's what I named my option builder, the second one right here. But even if I use the first one, if I have a maybe return 1, it's going to say maybe.run. It's going to wrap that around a maybe.delay because I implemented delay. And then it's going to put the maybe.return underneath that. That makes sense? That's the expansion.
What's return defined as again?
Return is just wrapping it as a sum.
Okay, so return sum.
Yeah.
Is that on this slide? Is that just like normal F#?
Yep.
Like type. It's a type I guess you're creating. It says type.
Yeah.
It's almost like it might be like an object.
Yeah, and this is in fact an object. This is a class definition in this case.
But I guess my question is there anything specific to this computation expressions or no?
No, computation expressions are implemented as classes.
Okay.
It ties into, so one of the things that F# supports is object programming, not to be confused with object-oriented programming. You can do object-oriented programming because it's in .NET and it supports almost all the features. There's a few things that have been kind of pushed to the side as like, we don't want this in the language, but for the most part, everything that's available in .NET is available in F#. Computation expressions actually build on top of the object syntax and classes, class definitions. And I'm going to get to a little bit more of that in a moment as we move on. So we looked at the expansion of maybe. That's this option builder. What about option monad? What do you think the expansion would be if I had opt return 1? I don't have a run defined. I don't have delay defined. What do you think it would be if it was opt return 1? How would it expand? Basically, it's just going to be maybe or opt.return 1. It's a very simple expansion. So basically what happens is if you define run, it will wrap the entire expansion in run, however you define that. If you define delay, delay will be wrapped inside of run, and then also inside of a few other places. Like it gets wrapped inside of combine, the second part of combine, it gets wrapped in several different places where it will delay some pieces from running until later on. So it's kind of an optional thing. If you implement them, it'll expand with it. If you don't implement it, it'll just ignore it and move on. So it's something to consider because you notice here you have some allocations, right? You're going to have a lambda allocated inside of the delay. And that can have some performance impacts that you wouldn't necessarily have if you're doing it with match statements or other types of syntax. So these are things to think about when you're building these things out. Here's a slightly more complicated one. We've got a let bang. We've got my maybe return 1 wrapped let bang value equals maybe return 1 and returning the value that I get out. No, the maybe is my option builder. So I created this class, option builder, and then created a single instance of called that I named maybe. It's just a singleton instance of an object.
Said the wrong thing.
Okay.
Didn't in an earlier slide, maybe your first slide, you had the word async?
That was yeah, that was back here.
Yeah, it was like your first slide. But
Right here?
that.
Yep.
Is that I get so is that async like it's a special keywords that you just block? the async?
Nope.
Oh, that was just.
It's an object instance.
Oh.
It's provided by F# core, but it's a singleton object instance. And what's interesting to note about this, and those are going to get to this momentarily, is computation expressions really are no more than an object instance with curly braces. So anytime that the compiler sees that, it's going to try and expand it, and if it has those members, it will expand it out. So you don't have you can add a whole bunch of additional members on your builder type that have nothing to do with the computation expression syntax. And it will be fine. If it has certain members, it will expand those out based on the syntax that you use inside the curly braces.
Okay, so then, okay, that makes sense. Going forward, we're back to the slide you were on.
Yep.
The word you had was maybe, which referenced your computation expression object.
That's right.
Is that the right, am I using the right
Yep.
nouns?
Yeah. Yeah.
Yes.
Maybe it's just the name of the instance. I could create another one called
banana.
maybe not or banana. Yeah, exactly.
Yeah.
And it will be the exact same thing. It'll just be a separate instance.
Right.
Fortunately, I can actually wrap those again around each other. It doesn't care because it's still part of Option Builder and it still knows how to expand those things correctly based on the types. So I don't have. I can make like I can rename. I could do like a let async2 equal async, and then have like some async 2s and asyncs kind of all mishmashed together.
Yes.
The types are all the same thing. So just because the instances are different doesn't really mean anything. It'll figure everything out and everything will still work. So again, it's just an instance with curly braces, and then there's certain syntactic things that it knows how to translate or expand. And that's really all that's happening here.
Like I'm coming from this background. Essentially, this is like a macro system.
Yeah.
Or like, yeah.
Yeah. Okay. And hold the question about why not just have a macro system, because that's at the very end.
Okay. Yeah. I didn't ask that.
Yep. So does this make sense, this expansion? So here we have a run delay, then we have bind because of the let bang. And I mentioned that the value, that's mine. I don't want to use this gets wrapped around this piece. So you see fund value is then expanded as a lambda, but maybe to return value. So what about delayed computations?
Can you go back a slide?
Yep.
Please. So in this case, maybe return 1 is actually going to evaluate to someone, right?
That's right.
And then the value is going to be someone.
No, the value there is going to be just the 1. It's going to lift that value out of the sum. So
Okay.
that really is, we didn't define the bind function. It's
Okay.
given to us by F# core.
Oh, you get it for free.
Yeah. So I'm basically just leveraging the bind, but it basically takes a,
So bind lifts the value out of its box.
yeah. So it's basically doing kind of like what we saw at the very top with the match
All right.
up here.
Mhm.
It's gonna basically kind of match some x and then take the x out, make it available in what happens next.
Okay. Sorry, it's a dumb question. I don't know.
No worries.
Can I do the most slide feedback?
Yeah.
On these examples where you have the thing and you have the substantial, you should go here. There's a comment that says substantial.
Okay.
No, it's like, or,
That's good feedback. Thank you. Okay, so what am I doing here?
Extending your initial definition of this type.
Yeah. How? I'm using what is typically a no-no in a shrug. You shouldn't use inheritance in object programming. It's more object-oriented programming. But in this case, it gives me an easy ability to not have to redefine bind and return again. That's all that's in option monad. So I'm just inheriting that base class and extending it that way. We'll talk about different ways of doing type extensions that are available in F#, but this is one way of doing this. We're inheriting and adding some new behavior. This does not change the initial option monad type. So my OPT instance will not have return from, combine, and delay, but opt_many will. And so the reason I put this in here is so I could do this thing here where I'm returning twice. And the second one, return bang, is enabled by return from. So it's really more of an example. If I'm returning 1 here, based on my definition of combine up there, if it is a sum, it's going to return whatever it has and not go forward. Right? So what should happen when we run opt_many? It should return 1 and stop, correct? not what we would expect it to do.
Yeah, that's what I would expect.
But what does it end up printing out at the bottom?
It's like it's in reverse order almost.
Well, it's not quite reverse order, but it's going to print and then say this is the result that I got back. But the question is, should it print at all? Maybe more to the point, do we want it to print that statement or not? I think we could probably argue that we don't want it to print if it doesn't go through that. If the first piece returns successfully, we want it to just return and not print and not try to do anything else with the second piece.
Seems reasonable.
It's not necessarily the right call, but let's say that that's what we want it to do. So how would we fix this? Well, it just so happens, if you notice this delay here, it takes in a function, this delay, where it takes a unit, and it immediately invokes it. And because delay is wrapped inside the second part of combine, it's going to take that second piece and immediately execute it. So it immediately calls delayed should not print and return none, and then matches against those two to determine if the delay is kind of being wrapped inside here. So that because it's returning immediately, it gives us back the none. So when it gets in here, it says, oh, I have a sum or a none. So it's already evaluated it too. It's already evaluated none. In order to do so, it had to print the statement. Right? So that's why it's going through there. It's not really delayed because I'm not really delaying it. I'm saying, I ignore the delay piece. I have to implement this because delay is required by combine, just in terms of how it's defined. Yep.
Okay, these members, like return from combined delay.
Yeah, those are all methods. Goes on that way. Yeah.
So are you inventing those names, or those are?
These are all part of the syntax of computation expressions.
Okay. Yep. So I got. So there's some finite list of 12, 52, or whatever.
Yeah.
And then that affects whatever's happening in the block.
That's right.
So so essentially lets you make a function async, or have it always return nothing, or do like you can do silly stuff if you want, but also you can do non-obvious things like this.
Right.
Like, yeah.
Yeah. And there are some, if you look in the documentation, there's some specific types assigned. They are flexible in what the types are supposed to be. Some of them are documented properly, some are not. But for the most part, they kind of align with what you would expect if you're familiar with the monad type of thing. And specifically, monad plus is available, monad transformers, like those are all kind of allowed within the generic operators that are, or the methods that you can implement. And there's a list of those in the documentation that lets you do these things. We're covering most of them. If we go back up here to option builder, I think the only two remaining that I didn't implement here are yield and yield from, and also quote. Quote deals with F# quotations. We'll talk about that, touch on that briefly a little bit later, but essentially quote gets pushed inside of run and wrapped around like if you have delay, it'll get pushed in there at the top level. So basically it'll transform whatever you have internally into a quotation. If you're familiar with list, it's the same sort of idea as like a list quotation. So you get like a syntax tree, and then run, you can then evaluate that syntax tree or transform it or whatever you want to run to do with it. So those are the members that we haven't implemented in this case.
Is that what the underscore is about? Does the underscore mean this is a special one?
No, underscore basically means ignore this thing. I don't want to give it a name because I don't need it. So it's more of an explicit marker of like, I don't care about this. The double underscore dot is like, I don't care about the name of the instance. So normally you would see something like this or self. You can, in F# you can name it whatever you want. It's a reference to the object itself. And in this case, it's typical to use double underscore to say, I don't care about the name of this class. Double underscore is in fact a valid name. So you can reference the class instance with double underscore. Yeah. But usually you use double underscore to say, I don't care about using it here. I don't need to reference itself. I'm just gonna not give it a name in this case. Also important, it doesn't have to be consistent. Yeah, we're not gonna get into that. It's getting into the syntax things. But I could name it like this, self, banana, yellow, blue, gray, like this doesn't care. It doesn't have to be the same thing all over the place.
But all those would still apply to your functions, right?
Yeah.
It's just that if you wanted to reference it internally, you'd have to use banana in one case, blue in the other case.
That's right. Yeah, within each method definition, it would use that whatever name I gave it in that one case. Yeah.
Yeah.
Okay, so in the case of the maybe builder, because of how I implemented delay, which you see, in this case, run calls the F, and delay does not. Also, look at the definition of combine. Because the delay did not execute the F that's passed in, the thing coming into combine is actually a function that has to be called. So on the none case, I then invoke the F there if I want to. I'm not getting an already evaluated option. I'm getting a function that returns an option. So again, the signatures change. They're not like a consistent static set of signatures. They can change depending on how you implement certain pieces. So delay and combine always get tied together. In fact, if you try to implement combine without delay, the compiler will tell you, build failed, you must implement delay with combine in order to do this. And in fact, the compiler can be quite helpful for anything. So for example, if I don't return explicitly, it'll tell me I need to implement 0. If I try to return several things, it'll tell me I need to implement combine. Like it'll actually tell me which members are missing. In addition to going to the docs to figure out what I need to do with it, the compiler actually helps me with computation expressions to know what I need to implement to satisfy the syntax that I'm trying to use. It will not do so for delay, run, or quote. One other member I forgot to mention is for. For, and as we saw with like the sequence expression, so for and yield kind of go together, where you're iterating and you're yielding out values, a sequence of values is kind of the idea. Bind and return are sort of the parallel set of terms. And they basically exist to make the computation expression look right, if you will. So if I'm dealing with something that's more like a collection, I'll want to use for and yield. They're essentially the exact same shapes as bind and return, but it just gives me a syntax that makes it look more familiar for a collection type of thing versus maybe a one and done, like an async or option or something like that, where I want to get a value out and then return some result at the end after doing some stuff with it. In addition to that, though, there's also for can also be implemented as like it takes a sequence of things and then you do stuff to kind of concatenate them together in some way. So it doesn't have to be only the corollary for a collection type thing. It could be like I'm getting a collection inside of my computation, and this is how I deal with that collection of things, essentially aggregating them within this new computation type. One thing we could do as well, we could make maybe, instead of using option directly, we could make it a wrapper type. This is a single case discriminated union, where it's a maybe, and it would have a function of unity option as the definition. If we wanted to make, like, force it to be delayed, this is similar to what the sequence is in concept. So it's you have to basically invoke the next each time you want to iterate on a sequence. This would basically turn an option or maybe computation into something similar to that, where it's always delayed explicitly. Very similar to the way async works, right? So async, you have to explicitly invoke it in order for it to do something. This would turn maybe into the same thing. So in this case, if we ran a computation this way, at the very end, we would get back something that effectively is a wrapped function that returns an option. I would have to then run that maybe computation explicitly in order to get anything out of it. Whereas, as we saw earlier, this is returning a value just by it being executed immediately. All right, so back to the one ring. How does the one ring factor into this? I kind of alluded to this a little bit. When a lot of people start getting into computation expressions and trying to figure this stuff out, most people in F#, the F# community, have tried to go for the Haskell do notation. Monads are everything. We want monads. We want everything to look like monads and work like monads. And some people have been successful. There's several libraries that do things like this where you get a common syntax, common set of patterns applied to make monads out of lots of different types. F# plus probably goes the farthest. There's some really interesting concepts in higher that use a lot of inheritance and object programming to show how you can do something similar with like applicatives and monads and a bunch of other things. And then there's an F# extras that has a whole bunch of these things implemented in a very common, similar way. But essentially, it turns everyone into the NAD school, where they're all trying to do, hunt down the ring and destroy the beauty of what computation expressions could be. So moving up towards the light, or at least a little more dimness, I guess, since we're underground with the dwarves. 7-foot dwarf lords in their halls of stone. And with this one, I wanted to talk about the pattern of query expressions. So query expressions look similar. We have a query here. It's got curly braces. We know that that's an instance of an object. The curly braces indicate, hey, there's some stuff in here I want to expand. Before, we didn't look at that number, but it's one that's built into computation expressions. However, now we see something that is different. Where and select. So unlike let and yield, which are kind of part of the F# language, where and select don't have any corollary to anything in F#. These are new things that were introduced. If you're familiar with C#, they introduced query expressions in the sense of, I can't remember actually the term that they used for it, but they basically came up with a from, something, where, select, like they actually made it a thing that's keywords in the language itself. Async await, C# has those as keywords directly embedded in the language. You can't manipulate them, change them. They mean a certain thing. They do expansions and whatnot, but they are baked in as keywords. Where and select here are actually not keywords. They're not in the language itself. These have been defined through the language and made available through the language, but they're not part of the language themselves. F# core, which is a library, it's the core library for F#, but it defines these terms. And I'll show you how that happens. So this, again, this is basically a query. So we're taking two sequences, finding out, it's kind of doing what kind of a join would this be?
It's like a filter map.
Yeah. So it's where these values are, is where x has a remainder of 1 and y has a remainder of 0 divided by 2. Add those values together and you get values like 13, 15, 17, 19, etc. So it's basically doing a query on this. There's no return, there's no yield. It does look slightly different than what we just looked at. Who's familiar with the reactive extensions, RX? There's implementations of this in a whole bunch of different languages. So most people are probably familiar with this in some way, with the observables, and they work a lot like enumerables. There's lots of talks from, 5 or so years ago where they were talking about the duality of enumerables and observables and how these things are essentially the same thing in different shapes, kind of different directions, if you will. So we can write a query expression in F#. And notice I don't have a where here. I have a zip. I don't think zip is actually in F# core. So I've created a new keyword, if you will. We just talked about they're not keywords, they're not baked into the language, but they are exposed through the language, through a language feature, essentially. I do have a select implemented, but I can do this for myself. And I'm free to create my own additional syntax, essentially. So I've created my own zip inside of this query expression. So this is going to take a sequence of 1 to 10 and a sequence of 11 to 20. If these were truly observables, this might be a really bad idea because you can't guarantee when these are going to happen. But given that these are coming from hot sequences, the values are already there. Zipping them in this way is not that big of a challenge. So I can get the values out, it'll subscribe to it, and print them all out to the screen. Using the pipe operator here. Of course, no output was produced because who knows why. And this is how this is achieved. So in this case, the RX query builder has been defined in part elsewhere. But I wanted to highlight a few of these specific methods. So first of all, type RX query builder with. This is called a type extension. in the actual implementation in F# control reactive, these custom operations are actually defined in the type itself. But in order to show it here more easily and also talk about type extensions, which we're going to get into more in a little while, I wanted to just kind of show what this looks like. So type query, RX query builder with essentially says there is a type. I'm going to add some things to it with the with syntax. Okay, so it's going to be treated from an F# perspective. And in almost every F# feature, it's going to consider these as part of that type now. Okay, so I'm extending the type. I'm not inheriting from it and subclassing it or any of that sort of thing. I'm just adding stuff onto a type, sort of like monkey patching, but it's not technically part of the type. It's just going to be treated like it's part of the type. Right, so monkey patching is you're actually adding things onto an object, and it is now part of that object everywhere it's available. This is namespaced and has to be opened and made available. It's not just implicitly part of the underlying object, at least not in most cases, if it's defined separately. All right, so aside from type extensions, we also have this custom operation attribute. So I've got normal methods here, called one select, I've called one zip. They have some additional parameter, like some attributes all over the place, and then an implementation. So RX provides the select method and a zip method. And I'm just using the ones that RX provides as an extension on the observables in order to implement this, these features. The custom operation is the thing that allows me to create new syntax. So I give it a name, and then I tell it how it should work. So there's a whole bunch of, I'm not going to cover all the different pieces, but there's a bunch of different attribute specifications that allow me to specify how should this thing work. So select is going to allow an in2 pattern. So I can actually do a select and then say in2. I could say whatever I'm selecting, I want to put that into a new variable to be used later, or a new value that I want to use later. I didn't use this in my example. I don't actually know why I would use select in2, but it is generally available on the way that these things are built. Projection parameter essentially lets me do this piece here. So really what this is supposed to be a lambda. It takes an X and a Y and produces a result. But that projection parameter says, you know what, project those values in and just make them available where you're using it so it looks a lot more syntactically nice. I don't have to put a lambda right in the middle of this thing. I think that looks nicer to have this X plus Y, would you agree? As opposed to having a lambda callback sort of thing splatted into the follow-up. So that's all that projection parameter is doing, is it's just making those values available, or those variable names available. Zip is like zip. Well, that's quite obviously the case. There's another one that's like is like join, is like group join. There's some of these that are like the type of thing you're trying to do is unique enough that it needs to know how to expand it. So there's just different values that are part of the custom operation that you have to say, treat it like this, treat it like that, and that gives you these additional features that you can use in your query expressions. But again, the nice thing is you can do a lot of different things with these. Speaking of extending existing builders, how about let's change the async builder. So how do monads typically work? The general idea is that you're going to await something so that you can then use it in the rest of the computation, right? So if you need to await something and then await something else, oftentimes you're awaiting the first thing so you can use it in the next await, and then you await that, and then you get the next, and you kind of chain these things up in a sequence, and you're awaiting over and over and over. But what if you actually have a couple of things you don't need to wait on? You can await all of them at the same time in parallel, and then use them all at the end, right? That's a reasonable thing you might want to do, and that's what this merge method is doing. So there is a proposal for the F# language to have an and bang, so you have a let bang and bang. However, it's not available yet. So we can do something like this, where we actually create our own and bang. The only problem is there is no way to use this with a let bang, because it's like zip, and because query expressions are essentially expecting something like a collection. for a list, you have to use for. So I'm just aliasing bind as for here so that I can have the for method implemented. It can expand properly. And then I have my merge. And now I can write code like we'll see in a second here. So I've got several async computations with a stopwatch showing like how long it's taking, just so we can see, does this actually work? Will it actually run in parallel or not? So this one's going to wait 1,000 seconds, or sorry, 1,000 milliseconds. This one will sleep for 500 milliseconds. And if we're using the monadic syntax, the let bang, it's going to await the first one, await the second one. And we can see that y does not depend on x, so there's no real reason to await, except that that's just how the computation expressions work at present. If we run this, we'll see that it starts in 7 milliseconds. After a little over 1 second, it returns. It kicks off the next one. Again, waits about 500 milliseconds, and then it finally wraps up. So with our hacky for double backtick and bang, just to note the double backtick. So there's a lot of things that are not invalid syntax in F#, like variable names that have spaces in them, for example. It would not be valid. But if you put double backticks around it, lo and behold, that is now a valid identifier. So interestingly, we used and bang in the custom operation. It didn't care. That was a totally fine string. In order to actually use it in our syntax here, we actually have to wrap it in double backticks. The syntax that will come out in F# core at some point in the future when this is formally supported will not require that. It'll be a new keyword that's available in the language.
So would you technically wrap like everything in double backticks after that word?
Could, yeah.
You wrap for and double backticks?
Not the for. That's a key. So for, in, and do are all keywords in the language.
But like return, does it have to
I think return being part of the defined syntax of computation expressions, the proper computation expressions, you couldn't wrap that.
Okay, so it's only stuff that you created.
Right. Yeah. There are something like we could do like a double backtick async and set that equal to async.
Okay.
But I mean, it's just it's an identifier at that point.
Yeah.
So
Again, I was just asking if that was like a global thing or that's unique to computation expressions. It seems like
it's not unique to, it is a global thing. It's just you can't wrap keywords in double backticks and have them still work. So they'll now be basically using double backticks is a way of getting around keywords being reserved. So if I want to use name something return, I can wrap it in double backticks, and now I can use that as an identifier. It won't violate the fact that that's already a keyword. So in this case, we can see that A and B start at the same time. B returns after 500 milliseconds. A returns after 1,000. And the total thing returns 1 millisecond later with the result. So these did run in parallel. And this doesn't always happen where they start at exactly the same millisecond, but they are, in this case, starting immediately at the same time. But it's a good example of showing that we can now extend the computation. So async, again, is a built-in one, part of F# core. But we've changed it. It's still using return, but it's now using the new for and the and bang that we added to do things in parallel. And this would be considered more like an applicative functor for those of you who are big into category theory. So what happens if we want to do like multiple of these things at a time? Besides just two, like we want to do 3, 4, or 5, whatever. So let's add one more, and we can see that we can still do more than just the 2. Right, so it's starting the first 2 at 3, the next one starts at 4. So there is a little bit of a tiny bit of delay getting to the third one, but overall it's still happening all 3 in parallel, even though the definition that we had up here appears to only accommodate 2 things at a time. Right, so it's able to figure out, oh, these are running. That result is an async. I can now make that result of the previous pair the X, and now we have another async in the Y. So it can kind of chain these up and kick them all off very rapidly. Okay, so one other thing about .NET is that async is the F# kind of normal way of doing asynchronous tasks, but .NET has a task type as well, just like the JavaScript promise. Can we use tasks? So if we're just overloading, we're going to create a method overload in a computation expression, we can use tasks just fine. there's already an async await task that's available as a function you can call to await the task and turn it into an async so you can await it normally with a let bang in the async computation expression. As you can see, is happening right here. The tooltips still aren't showing up for me. We didn't implement that overload, but can we overload a custom operation like merge? So it turns out, and I just found this out at OpenF this year, really by accident because I forgot to add the attribute. If you add the attribute here, you will see this. A custom operation and bang refers to a method which is overloaded. The implementations of custom operations may not be overloaded. And bang, var, collection, blah, blah, blah. So you can't do it if you add the attribute. However, due to the glorious nature of method dispatch in .NET, if you don't put the attribute on there, the attribute has to be on one of the merges. We already have it defined on the merge we defined earlier. And I overload merge, the object method dispatch figures out which merge to call. So you can effectively do overloads of methods. In this case, I'm within an async computation, and I could do overloads of merge that have two asyncs, two tasks, an async and a task and an async, and mix all these things up and have it all basically turn into asyncs at the end and run just fine. Which is kind of a nice way to do things. I have been told that this is in fact a bug. There is formal work going on to make custom operation overloading more like correct. But it is possible to do this today, which is kind of exciting and fun. And then another thing to note here, this violates the normal idea of a monad. A monad is like a type, like an async, all the way through. Here we're exploding that and saying, well, this thing is like an async, so it's a task, and it can also play in the same playground as the async can. There are other limitations to these, specifically with query expressions. There's a lot of things you can't do. Like you can't do if then branches without an else in certain situations. You can't. I'm forgetting all the details. There's this link actually points to like a section of the error messages that you'll get back. They're not well documented. You basically have to go and look in the compiler code and find here are the error messages that will be thrown if you try to do this, 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 or this. And when you try to do them, the compiler will tell you that that's not allowed. But there's just like some weird restrictions on what you can do with query expressions. Again, because they were initially built with the idea of being a query over some sort of a data source, so it's expecting some sort of a collection. It's expecting to use a for around it. So there's some limitations in what you can do with this, but the flexibility and the power are actually quite nice. As we will now see. So 3 rings for the Elven Kings under the sky. We've come all the way up to the surface. We're now in the beautiful golden light of Lothlorien. And now we're going to look at how F# computation expressions enable domain-specific languages. So we've looked at all the building blocks to what we can do. And so this is going to be looking at a lot of examples of what people have done with this stuff. In some cases extreme, in some cases just extremely handy and useful. So anybody familiar with the build tool called Shake? It's actually written in Haskell. Doesn't appear so. Well, somebody built the same thing in F# using computation expressions and called it Shake with an X instead of an SH. So this is an example of a build here. So you define different rules within a shake script computation expression. Rules obviously is not a built-in keyword. However, it is a custom operation that in this case takes a list of tasks, and it's got custom operators, not to be confused with custom operations, in the form of a less than equal and a dot dot greater than and some other things. But basically, you can create like your own little syntax. It's mimicking what the Shake build tool uses within F#. And this usually is run as like an F# script. You can use this to define your builds. It doesn't have to be just .NET. Obviously, there's a Shake.NET plugin for this, and so on. There's a really handy testing library called Expecto, where the tests are effectively first-class citizens. So this one is a test that is a computation expression. This one's interesting. We talked about how a computation is an object instance. What do you think is happening here, though? Is this test, is it an object instance in this case?
That's what it is.
The test itself. So the let test is a value. It's being assigned to the test computation expression.
Is it a function?
What's that?
Is it a function?
It is a function. Yeah, so test is a function that returns a test. So in this case, every time you define a test, you're going to create a new instance. And that string that's going in there is basically a constructor parameter that gets passed through, and it constructs a test case instance underneath. But again, it's just essentially something that becomes an object, has curly braces after it, can be expanded. In this case, the type is actually unit. So earlier we looked at option, we talked about async. The type of this computation expression is unit. Because expect doesn't actually return anything. The test is an instance, and you can package these, repackage them, pass them around and everything. But the actual result of this is actually going to be unit. It's just going to run and push some output out somewhere, and that's it. It's kind of an interesting concept, because you don't typically think in functional languages about things that just have side effects and that's all. But that's effectively what this test runner is going to do. He likes writing, this is effectively like assembly for .NET. So the common intermediate language, there are actually several implementations of generating and emitting IL operators and operations using computation expressions. This one is yielding out those instructions. There are others that make those actual keywords using query expressions instead of yielding them out each time. And then here he's piping it to a toDelegate, which is going to call reflection.emit. That basically generates IL into the assembly, the running assembly. And then you can execute my function 1 as a function that exists in that assembly after this has been executed. Kind of runtime compilation. You probably normally wouldn't want to write IL directly like this. It's sort of a kind of a fun, we can do this if we really want to, sort of thing. But it really exemplifies the power of these things. I think a year or so ago, I did a talk on Freya at this user group. Freya is effectively an implementation of Erlang's web machine in F#, or something similar to it. It's not exactly the same thing, but it basically uses computation expressions to expose all the holes you can plug into the state machine of HTTP. There's a router implementation, a Freya machine, which is the thing where you define, like, here's an HTTP resource, and here's the methods it supports, how it responds to those different pieces, and et cetera. This isn't a talk on Freya, so I'm not going to go into too much more detail on that. But you can see that, like, methods and handle OK and resource are all custom operations that are being used. In this case, the Freya router references the machine that we defined up above. So the resource is saying I'm using the Freya machine called machine at hello/some name to run. Since I gave this talk at OpenF#, there's an MVC framework called Saturn. It's based on Elixir's Phoenix framework. There's probably a lot more we could do on this one to clean up some of the, you'll see, like, there's these lambdas of fun context, and then use some things in there. Some of this is currently to support the ability to specify things like ID or other route parameters. But it does make it kind of long. But you can see the controller has, like, index, add, show, edit. Those are effectively the root, something with a parameter, etc. And then there's an application computation expression where you have things where you can hook in different pipelines, tap into a router, specify the URL it's going to run in, additional plugins you want to use, like gzip, static memory cache, etc. So this basically gives again, a DSL inside of F# for how to build an MVC application. So how is some of this stuff possible? Because some of these things are doing some pretty complicated things. And probably the best example to think through what's happening under the scenes is with the built-in query expression. So we just kind of glazed over that the first time. But if you look at this, we're looking at a query expression over an XML document. So this is using a lot of the link stuff that's built into, or that's available through .NET system.link, or system.xml.link, system link XML, can't remember which one it is. But effectively what's going on here is it's going to, in this case, it's outputting a sequence. But if you look underneath the hood of what's going on here, this is actually turning everything into quotations and then processing those quotations in order to get back the results. So this query expression can be used over, say, like the SQL or Entity Framework, and used to generate something that goes down into a different layer. In this case, for XML, it's going to turn into, I don't know how the XML stuff is implemented. But it could be, depending on how you have this stored, it might actually go into like an XML query, like an XQuery sort of language transformation, or XSLT or something to actually hit the XML and pull back some results. Yeah, there you go. Yeah. There's basically a string literal in the strictest sense of the term. So effectively, you can do almost anything internal to that computation expression. It doesn't have to be whatever type you've defined at the top. If you think you're working in, you can actually work in something different underneath. And that's sort of how like the Freya graph piece works. So this massive HTTP state machine graph, I think this came from the Web Machine project. There's different pieces of that graph that define like the different state transitions that can happen within there. And Freya essentially implements like a bunch of these pieces as like optional graph nodes that you can plug into. And part of what Freya ends up doing is as it runs at runtime, it determines like how much is actually used and then shakes off the rest. So it optimizes for performance at runtime. So you might think, oh, it's a static state machine, it's going to run through all the steps. But actually, because it's an abstraction over something more complicated, it can actually look and see what have you tapped into, what pieces are you using. Oh, you don't need this? Fine, we'll just chuck that. We won't use this at runtime. And it can actually optimize underneath the hood. All right, so that's kind of a wrap on the computation expressions. Again, the goal of this was to kind of show like what can be done, what are some of the big patterns about it, how does it work, not necessarily in a deep dive sort of way. I hope I gave people kind of an idea of what F# can provide in terms of extending the language through these very powerful and expressive computation expressions. Yes, sir.
In general, in practical uses, do you create these, or do you like that for like library?
That's a great question. I have not been using them as much in my own code, even though there's been lots of times I'm like, I should probably put a computation expression in here. It is probably, unless you're doing something very minimal, like the bind and return opt monad type thing that we showed at the beginning, it's probably best to have your own. There are some libraries out there. I showed a few that were for like kind of monad specific. There's another one for what's called railroad-oriented railroad-oriented programming, where you kind of push your errors forward instead of throwing exceptions, called Chessie, that a lot of people use. But the kind of the one where I showed the option builder, where I had 0 is none, and the combine pushed through the sums, and if it was none, it went to the next one. That's definitely a like, you may want this, you may want something different. There's multiple ways to implement the builders when you get to the more expressive pieces, like you want to have multiple return values or not. So it actually, and most of them are not that difficult to write. And so for the most part, for most uses, I would say you generally want to write your own. And it's just an object type. You can share them across classes if you want. You make an internal library. If it does work for you, then use one that exists. But a lot of times it's maybe more like better for you to use one that you've written for yourself.
So like, you use them like a tackless?
We use a few of them. We used to use them more. A lot of we started actually splitting up functions to be smaller functions and then just using pipelines more, which is totally fine. As long as like the main reason we were doing it originally was we were trying to avoid all the arrowheads. We started getting like, lots of long, deep nested match statements and other things, but kind of breaking those into smaller functions can help you avoid some of that pattern anyway. So right now, I don't think we have as much use of them, but we're working on a project and we just introduced, I think, the async result computation expression, and it cleaned up the code significantly. So that's kind of matching two different types, async and a result, and combining them so you don't have like lots of joining things back together and mixing them all back together. I didn't really talk about that sort of a pattern where it's kind of more like a monad transformer type of thing. We have like async and result, both of which can be monadic, and how those tie together. But that's like one use case for building your own computation expression. Yes, sir.
So one thing that you, I guess, were going to talk about but never did was kind of this pattern versus macros.
Yes.
Yeah. So that.
So
I was wondering if you were just like waiting to talk about that.
basically, yeah. I was gonna hit on it. So one of the design goals of F# was to keep everything simple. There's a paper that's coming out that Don Syme, the creator of the language, is writing that goes into the history of the language, and he talks about like why certain decisions were made, and most of the mistakes that he points out that they made along the way were things along the lines of like, why do we have an async and a task? Why do we have tuples defined one way? They do tie into .NET tuples, but then we have struct tuples, and how do we, like all this thing of like we're building on a platform. That was a good decision. But then some of the places where there's like two things and then we have to try to bridge the gap between them, how do we make that work better? Is one of the areas he sees. He thinks that they maybe could have done a better job of tying together better. And macros, on one hand, would be really challenging to implement in only F# when it's not supported in the .NET runtime as a general rule. The second piece of that is that were they to do so, that would also have required some like either compiler plugin type architecture or like a multi-stage compiler architecture that just would increase the build times. People already complain about the build times for F#. It's not that bad, but some people think it's a lot slower than C# or whatever. There's certain things you can do in F# that do definitely slow down the compiler, and they kind of relate to things like macros. They're called statically resolved type parameters, and they essentially code gen based on kind of matching method definitions and types and things like that. So there's already like indications that doing so would actually make the compile times longer. And then lastly, macros tend to not play that well with static types. There's actually some research on this with macro ML and meta ML, but those haven't made it into like a mainstream, like here's macros all the time. Some people have played with the idea of macros in F# through type providers, through additional compilation levels, kind of code genning as you go. But even those are kind of like ways to get extensibility into the language without having to go full scale into macros where you're kind of just opening everything up to everybody. So it'd be similar. It'd be interesting to look at like something like Lisp and see, can you create a typed Lisp succinctly and correctly? It actually works really well. I think type racket works pretty well. There's some examples that do some of that decently well, but I don't know, the ML style languages, it's macro ML and meta ML have shown that it can be done, but they're not, again, kind of the mainstream thing, and they haven't made their way back into the dominant languages like OCaml or F# or any of those. Yes.
So I kind of started off before we started the talk. I kind of had this whole thing about abstractions and helpful abstractions and unhelpful abstractions, and it sounds like this generally is a helpful abstraction where you can really model something that you're trying to compute. It's sort of in the language of that domain or whatever. That is definitely very helpful because 6 months later you will come back to it and be like, oh yeah, okay, I kind of know what's going on here. also feels like this is a tool where you can really shoot yourself in the foot, right? Where you put too much magic in the box, and then no one's really sure how the magic works anymore. How do you, like, I guess my question is, how do you have good style about this? How do you make good choices about when to use this and when not to use this? I come from a world of Erlang, which is also like super explicit generally. There's very little magic in Erlang. It's like literally what's in your editor, that's what's going to be executed. There's no macro facilities or whatever. I mean, there technically are, but they're basically compiler substitutions. But I guess that's my question. Like, how do you have good style around this kind of tool? Like, how do you decide when it's appropriate and not appropriate?
Yeah, it's a great question. So one thing would be if you have an arrowhead pattern showing up, it's pretty simple to get rid of that and make it flat by defining one of these. So that's a great time to like look at implementing one. You don't have to implement all the members. I showed a bunch of the members you can implement, but most of the time implementing like bind and return or for and yield is sufficient to get by. Implementing the fewest members possible to solve the problem is one way. So it's allowed for one, which is great. And then the fact that you can't really like combine these things easily, like you have to define a computation expression per use case, prohibits you from getting too crazy in terms of how messed up you can get. The implementation is pretty simple. It's just a class definition. You can go easily read the class, see what it's going to do. The expansions are pretty easy to see. If you ever get, like, one thing I've been doing as I've written some of these in the past is I put like print statements in the members. So every time I got called, I could see what was being printed out, what was the order they were being called in, and figure out like, what do I need to tweak here and there to make it work better. And then maybe comment them out. Most of the time I'm deleting them because it's not that difficult to add them back in if I need to. But for the most part, most of the ones that are the most handy and useful are really small, really easy to write. They're defined as an object. So it's not that complicated to go read that code and just know that this is going to translate in this way. It's a very standard thing. When you get to query expressions, now you're already going into like a more deep, more challenging thing. So if you're going to write a query expression over something like SQL, like maybe you want to write one for Postgres, it's different from, for whatever reason, you want to have something that's very specific to that versus Andy framework or link to SQL. You're going to have to know how to translate F# code quotations into a query for that language.
Right.
I think people are using something like that for Mongo at some point. I don't know what the state of that one is now. There are lots of things like that. So you already have to have kind of a domain-specific knowledge about that, which may be helpful to your team. You want people to be able to write queries over some data store without having everyone be an expert in how to write queries in that data store. Right. And most people know how to write SQL. So writing one of these over SQL, maybe not the best use of your time, especially when you have things like type providers that can maybe do a better job.
Right.
Type providers are another one of those things where like you have to have like a very deep knowledge of how those work to write one that works well. And I think the query expressions can get in that direction. The RX one, for example, is more like the computation expressions. It's pretty straightforward. It's just calling certain operators. So instead of doing like a dot select many dot where or filter or whatever the different methods are in a chained way, I'm basically just putting it inside of a computation expression. So it looks more like an F# thing than a C# or .NET thing. But it's otherwise basically the same thing. Once you get to like Saturn and Freya and Expecto and some of those, now you're getting into something a lot more challenging where you definitely want it to be a library where people are supporting it. I look at Freya still and my mind kind of bends every once in a while because it's the implementation is, because of all that it's trying to do to make it fast, to make it more efficient, it's doing a lot, which is great for people using it, but certainly much more challenging to support.
Sure.
So I think lean towards the like, what's the simplest thing? And I feel like the computation expressions try to push you in that direction. It's easy to do this, do that. It's easy to do this, do that. It's a little more complicated, but still worthwhile, do this. Doing something really big like Freya is probably not worth everyone's time to try to build. So like join a team trying to build something like that and make it available to others, but then a lot of people will probably use it, but few people will probably work on it.
Sure.
But I think that's more the exception. Like the ones that I pulled in as examples are kind of probably some really good examples of like how far you can go, but not necessarily the thing you would see most people using them for. But they are really handy for like even just the simple tasks that they're really good at. So I hope that's kind of it depends answer, but
No, it's a good it depends answer.
okay. So another common question is, will F# ever get type classes? It's kind of similar to the macro question, but in the different direction towards Haskell instead of like a list sort of thing. And there is actually a paper called Classes for the Masses, and the types, they figured out that the types for type classes, given a certain signature and everything, are actually valid types and definitions in F# today. And with similar changes for C#, they could actually do, I think with no changes to the runtime, or maybe there's like very minimal changes to the runtime, they could actually get this in C#. And this gets back to the whole language design thing. They didn't want to do anything new in F# that they can't do generally in C#, especially if it was likely that C# would want to get it. So the Classes for the Masses paper has implementations in Roslyn, the C# compiler, and F#, where this is probably going to happen. It's just a matter of when, and a lot of that's going to be driven by like when does C# do it, when do the runtime things happen, if there are any that are going to happen. There are other similar discussions about bringing in additional changes to .NET in general and the CLR to support additional like higher kind of types sort of ideas, not necessarily those, but similar types of ideas into .NET. And again, once that happens, F# will probably adopt some more of that stuff. So the answer is probably yes. It's more just F# is trying to take a more conservative approach and bringing these things in as all of .NET gets them and do it in the .NET way instead of trying to make it an F# only sort of story. So, and then I got a whole bunch of references for people who, the slides are online on my GitHub. I can post this out in the comments on the meetup.
Yeah, that'd be great.
If people want to see it.
Absolutely.
Specifically, I want to call out, this was a video we did when it was first released, like on Community for F#, like, it's been a long time. It's actually really good. I've gone back and watched that many times. The F# Computation Expressions Zoos, a paper by Tomas Mitratech, talking about kind of the same sort of thing, like different types of patterns. He goes into 3 specific patterns, slightly different than what I did. And then just generally for F# for Fun and Profit is a fantastic website, even if you're just interested in comedy. So I highly recommend those things. Any other questions? Comments? Thrown tomatoes? Anything like that?
Thanks.
All right. Yeah. Thank you.